Today we are going to discuss a couple of reactions. One is the Dieckmann condensation and the Friedel-Crafts reaction. We know all these reactions from our previous semesters, but this time we are going to highlight some modifications of these traditional reactions which have made them a more sustainable version of whatever we used to perform maybe 40-50 years back. So what is Dieckmann condensation? Dieckmann condensation is a variation of Claisen condensation. In Claisen condensation you have an enolate derived from an ester reacting with another molecule of ester, and after the ejection of the alkoxide you get a 1,3 dicarbonyl compound. It's one of the most useful name reactions of carbonyl chemistry to form a carbon-carbon bond. Like aldol, it involves an enolate, but this time the enolate is derived from an ester, and like aldol it also involves an electrophile. Instead of a ketone or an aldehyde, we have a ester carbonyl as the electrophile, which also carries a leaving group. If we do this reaction in an intramolecular fashion, where two esters are present on the same compound, such as this molecule which is known as the diethyl adipate, the ethyl ester of adipic acid, and we treat that with sodium ethoxide in ethanol, then the ring closes by forming an enolate from this side and closing down the ring by attacking this carbon, so that we may end up with 1, 2, 3, 4, 5, a 5-membered ring. And the reaction has this peculiar property that one of the hydrogen is in fact much more acidic in the product compared to any hydrogens present in the reactant, and therefore sodium ethoxide will deprotonate this hydrogen and form a salt of the 1,3 dicarbonyl compound. This is actually good for us because thermochemical analysis of Claisen condensation reveals that this reversible reaction, in fact, up to the penultimate step, it favors the reactants, not the products. But the deprotonation of this most acidic hydrogen provides the driving force to bring the reactants to the product side. So if you do not have this sort of a hydrogen present at this carbon, your Dieckmann condensation or Claisen condensation will fail if you are using sodium ethoxide as the base. In that case you have to use a much stronger base like PH3Na or something like that. And of course you cannot use sodium hydroxide here. Can you use sodium hydroxide as a base here? Can you use that? What could be the problem of using sodium hydroxide in water in this case? What could be the problem? Does sodium hydroxide react with ester groups?
No, sir.
It hydrolyzes the esters, no?
Yes, sir.
The BSE2 mechanism, if I think in terms of simple esters, then the mechanism is BSE2, and it will actually hydrolyze those carboxylate esters, carboxylic acid esters, and ultimately it will give rise to carboxylates from which you cannot possibly derive an enolate, because sodium hydroxide is nonetheless, in terms of organic standard, it is a strong base, but to generate enolate from carboxylate you need a far stronger base. So Claisen condensation will fail if you use sodium hydroxide as a base. But you can use non-nucleophilic basic compounds such as PH3Na or something like that even if you do not have this sort of a hydrogen present here, Claisen or Dieckmann condensation will take place. But if you are using sodium ethoxide, then you must have this hydrogen present, otherwise the equilibrium will not favor the product but will favor the reactant. Clear? So
Yes.
that means that you need to have a acid workup step for the isolation of the product. And this being a 5-membered ring with a carbonyl ketocarbonyl present, and with that we have a carboxylic acid ester at the alpha carbon. So this is a beta keto ester. In terms of the CO2, this is the alpha carbon and this is the beta carbon. So this is a beta keto ester. And these beta keto esters, they can be hydrolyzed, just as we talked about just a few minutes earlier. You can use sodium hydroxide in aqueous alcoholic solution, and then you can hydrolyze them, and this will give rise to the corresponding potassium salt, which on acidification will liberate the beta keto acid, and upon warming these beta keto acids have a tendency to undergo decarboxylation, giving rise to the enol form of the corresponding ketone, which automerizes to, in this case, cyclopentanone. So this is a technique for synthesis of ketones, cyclic ketones, starting from the diester. If we start from, say, adipic acid diester like diethyl adipate, or the pimelic acid diester, diethyl pimelate, then these reactions are more or less good yield. We get good yield. But if we are thinking in terms of closing down the ring and achieving 10-membered, 11-membered, 12-membered large ring like macrocycles, then those sort of intramolecular reactions are quite forbidden entropically. For successfully carrying out the cyclization that leads to formation of large rings, we have discussed about the high dilution principle, where the concentration of the reactant is so low that the entropically favorable, or I should say less unfavorable, intermolecular reactions, those are subsided. Those are unfavored because you have deliberately put the concentration of the material very, very low, and that is why people call it high dilution. So this molecule, or the molecule which will lead to the macrocycle, won't have any opportunity except reacting in a intramolecular fashion. But not such a problem for 5-membered ring formation or 6-membered ring formation, because the penalty that you pay in terms of losing the conformational entropy going from an acyclic to a cyclic reactant to a cyclic product is not that high. But for a microcycle, that penalty is very high. So this is one typical example where diethyl adipate has been converted into cyclopentanone, and this is one of the classic example that people all over the world cite when they discuss the Dieckmann reaction. So can you tell me from any starting material from which we can get this diethyl adipate? Of course, adipic acid, esterification of adipic acid would give rise to diethyl adipate. But what about the adipic acid itself? How can you get the diethyl, the adipic acid? How to get the adipic acid? So I am looking to get this acid, okay. How can I get that? Any idea? From where should I get this? শুনতে পাচ্ছি না, একটু জোরে বলো। Cyclohexene, yes, sure. So we can just remove these carboxylic acids groups and form a carbon-carbon bond here, right? And then you have a double bond here. So what sort of reaction are we talking about here for this conversion? we can do a simple ozonolysis under oxidative workup. So this will give rise to the adipic acid, the precursor of the diethyl adipate. But how to generate this? Can we think of in terms of dehydration of alcohols? So can we start from this compound? What is this? Cyclohexanol,
No.
right? And how to get this? You can either do it from here, from cyclohexanone, or if you are looking to get it from natural sources, you can start from this one. And what is the most useful technique for synthesis of phenols? No. Cumene phenol, yeah. So you start from this one, right? The rearrangement itself that is involved there is called Hock rearrangement, HOCK Hock rearrangement, the cumene phenol pathway. You start from this, and exploiting the radical stability at the allylic position, you introduce an oxygen, a O2 group there, so it gets a peroxide, and then you rearrange it. And not only do you get phenol, but you also get acetone, two of the most important organic chemicals in chemical industry. So if we start from cyclohexanone, we can end up with cyclopentanone. So cyclohexanone is reduced first to cyclohexanol, then dehydrated to cyclohexene, then converted to adipic acid, then converted to diethyl adipate, then subjected to Dieckmann condensation. Subsequent decarboxylation will give rise to a ring contracted product. Here is another example where a heterocyclic ring has been constructed. So this means that these two CH2 groups are equivalent. We can deprotonate any one of them. Let us deprotonate this one, and this ring closes. This time we are getting 1, 2, 3, 4, 5 and 6 membered ring, and this is done in sodium ethoxide in benzene and then worked up with HCl, because as you know, this proton would be abstracted after the Dieckmann condensation is over. And so to get the product, we have to acidify the resulting enolate, and it happens to be so that it also has a tertiary amine which will be protonated under this reaction condition. So I will basically get a hydrochloride salt. We have already discussed many aspects of Dieckmann condensation in terms of the parent reaction, Claisen, etc. But what are the disadvantages that Dieckmann condensation particularly has? One disadvantage is that you are using sodium ethoxide, or you are using stronger base than sodium ethoxide, so that's probably not a very good idea, not sustainable in terms of green chemistry, because that kind of strong base may lead to waste treatment problem and disposal problem. Byproducts may sometimes form. Cyclic esters that have alpha hydrogen may involve in some sort of aldol condensation by themselves and leading to byproducts which will compromise the yield. You definitely cannot use hydroxide, and therefore the use of water as your reaction medium is completely excluded, because if you have water and you have sodium ethoxide, then there will be hydroxide, and hydroxide will, what will it do? It will simply hydrolyze the ester, and once the ester is hydrolyzed, then it's gone. There is no way you can close the ring or anything like that. As byproducts form, you have a tedious product separation step involved, so that's not very good either. So these are the non-green aspects of the Dieckmann condensation. However useful the reaction is, there are certainly some limitations. So chemists have devoted a large amount of time to come up with greener alternatives, and they have done quite a bit of work on this. We will discuss only a few. let's first discuss the ultrasound assisted Dieckmann condensation. This is a diester, it's treated with potassium taken in toluene, and the reaction is done at room temperature and it is over within 5 minutes, provided you have an ultrasonic machine to do this reaction in. The yield of the product is also very good, 80 to 90%, so that's pretty acceptable. And the potassium that is used is under sonication, it is converted into a blue suspension when you sonicate that whole thing. And not only Dieckmann condensation but also the Thorpe-Ziegler cyclization, which involves cyanide compounds. Those reactions has also been done under ultrasonic bath, in ultrasonic bath. So what is the green context of this? We have not used any so-called strong base, we have used just potassium. So the waste disposal and waste problem and disposal problem is kind of taken care of. Reaction is carried out at room temperature, which means that you are not using any sort of heating or energy expenditure wise. It is a very efficient process and non-renewable energy sources are not involved. That's good. Product separation is easy because byproduct formation is less, and reaction time is very, very short, and the yield is very acceptable. Fine, okay. Any sort of questions? দিলে লিখতে পারবে তো?
হ্যাঁ স্যার।
Okay, let's go to solid state Dieckmann condensation. And as we have discussed many times, solid state reactions are sometimes much more preferable compared to solution phase, because solution means you have to use a solvent, and sometimes those solvents are not good, they can have detrimental environmental impact, and once you do a reaction in the solvent, it is either recycled or it has to be disposed of. Recycling can be done a finite number of times and then it becomes unusable, so you have to get rid of it. So solid state reactions can do away with all these sort of problems. So let's say we have taken diethyl adipate or diethyl pimelate and done this reaction in solid phase. This is done in simple mortar pestle. So you take a powdered base like potassium tertiary butoxide, which is a stronger base than sodium ethoxide, and then you mix the diester and you take those things in a mortar pestle and then grind it for 10 minutes, and it will become a paste, and then finally it will solidify, and then you add, because this is Dieckmann, the final product is an enolate, so you have to use some sort of acid, so you use the tosic acid, hydrated tosic acid, and then you distill. When you distill in 60 to 70% yield, the diester comes out. So this is how this reaction is done. Okay, so see, when n is equal to 2, this is a 5-membered ring. When n is equal to 3, this is a 6-membered ring. So you have started from this compound. When n is equal to 2, it is diethyl adipate. When n is equal to 3, it is diethyl pimelate. You can also use like sodium tertiary butoxide or potassium ethoxide or sodium ethoxide. All these bases you can use. What are the green contexts? Solvent free condition, therefore no solvent is involved. Product separation is very easy, method is cost effective and eco-friendly. Okay, so these two reactions we have discussed in terms of Dieckmann condensation. The final name reaction of this section, and we will be discussing rearrangement reactions in next classes, but this time we have a Friedel-Crafts reaction. This is one of the age-old reactions, very old reactions, and one of the earliest examples of carbon-carbon bond formation, particularly gives access to the realm of aromatic reactivity. So it's a general aromatic electrophilic substitution where the nucleophile is a aromatic ring and the electrophile is a acid halide or a acid anhydride, or you can also use alkyl halides. If you use alkyl halides, then the product is alkyl benzene, and if you use a source of a acylium electrophile like acid halide or acid anhydride, then you end up with a aromatic ketone. This is one of the most robust technique for the synthesis of aromatic ketones. Obviously, the reactivity of the aromatic ring is not such that if you mix those things they will react. It's not like that. You need to have some sort of catalyst. The generic catalyst that people know about, or that was first explored by Friedel-Crafts, it is the anhydrous AlCl3, but over time many catalysts have been developed, and they have done quite well in terms of yields, or in terms of reactivity, in terms of selectivity. So some of them are like boron trifluoride, FeCl3. FeCl3 is particularly impressive because of reasons that we have discussed earlier, and we will probably allude on this a little bit more. TiCl4, SnCl4, all these things have been used. So this looks okay, but certainly there are certain disadvantages or non-green context associated with this reaction as well. The conventional catalyst is AlCl3. So when you do the reaction after your product has formed, it is recommended that you dump the whole thing into a ice water HCl mixture. You can get rid of the HCl, for sure you can get rid of the HCl. You can just dump the whole thing in ice cold water or crushed ice, but the AlCl3 that is present there, it will form aluminum hydroxide, and that is a gelatinous precipitate. To isolate your product from that gelatinous precipitate, it becomes a tedious process. So it is recommended that you use HCl, and if you use HCl, then the aluminum hydroxide is decomposed under acidic medium, and salt formation takes place, which is soluble in water, and your organic product is easily isolated. But all these things will generate some sort of ionic salt, which will ultimately end up in the environment. So the byproducts of the isolation process is not very good for sustainable development or sustainable chemistry, and this waste treatment problem is hazardous, and you will have to take care of it. For synthesis of linear alkyl benzenes, the challenge is very high because of two reasons. One reason is that if you take linear alkyl benzene, that means there is no branching, and your electrophile will be something like RCH2CH2CH2CH2 plus, or RCH2CH2CH2CH2X, leading to a formation of a primary kind of carbocation, and that primary carbocation has the tremendous tendency to undergo rearrangement into a more stable tertiary form or secondary form. Any way it can stabilize itself, it will try to stabilize itself. A very common question in semester 3, semester 4 you have faced when you were learning aromatic electrophilic substitution, and subsequently in the next sem the rearrangement reactions, that to prepare N-propyl benzene, you cannot use N-propyl chloride as your electrophile. Do you remember this question? Because ultimately from the N-propyl chloride you will get the isopropyl carbocation after rearrangement, and eventually the major product would be like cumene, isopropyl benzene. So that is a surely it's a problem. However, this problem can be somehow mitigated. We have learned one technique that use a weaker Lewis acid, weaker compared to AlCl3. So use ferric chloride, FeCl3, so that the full blown carbocation is not generated, but enough electron deficiency is generated on carbon so that the benzene ring or the concerned aromatic system can make its nucleophilic attack there. Another way you can do this reaction, which we did not talk about, was to use catalytic hydrogen fluoride. Now this is a very nasty substance. Not only is it bad for you, but also it is very bad for the containers or the instruments that you are using to perform this reaction. This is extremely corrosive, extremely hazardous for health, and extremely toxic, and therefore special type of containers, special apparatus are needed to handle this catalyst. But this catalyst is very effective for generation of linear alkyl benzene. So we would like to have developed methods where we can generate linear alkyl benzenes in high yield without using the toxic HF. The problem of alkylation is actually twofold. One we have talked about, the rearrangement. The other is over alkylation, because once you introduce an alkyl group onto the ring, due to the electron releasing nature of the alkyl group, the system is actually more activated towards further aromatic electrophilic substitution. To stop that, you need to use large excess of the substrate and limited amount of the alkylating agent. But all these things are not stoichiometrically or environmentally sustainable all the time. I mean, 40-50 years back you could get away with it, but this time you will probably not. So this rearrangement is a problem, this over alkylation is a problem, at least as far as alkylation is concerned. You need to have higher energy inputs for this reaction to get high yields. Large quantity of catalyst will be required if you have these groups on your substrates, because these things will have a tendency to bind with the catalyst itself, and then that catalyst becomes useless. So you need to use like 1.1 equivalent of catalyst, so that one equivalent complexes with the OH or the NH2 group that is present in the substrate, and the rest 0.1 or 10% excess that you are using, that is actually acting as the catalyst only. So this is another problem. Electron withdrawing meta directing group, if they are present, the reaction is a complete failure. Do you remember this question, that nitrobenzene can be used as a solvent in Friedel-Crafts reaction?
Yes, sir.
They used to ask this question, why? Because the implication is obvious, that they are trying to point out that you also have a benzene ring in nitrobenzene, and benzene rings are supposed to act as nucleophiles in aromatic electrophilic substitution such as Friedel-Crafts reaction, but nitrobenzene can be happily used as a solvent. Something which is being used as a solvent cannot react with any of the reagents or the products or something like that. That is a given. If it does that, then it does not qualify as a solvent. That's because nitro has a tremendous electron withdrawing power, and that is why the ring is so deactivated that even a super electrophile like a carbocation, it does not react with the nitrobenzene. It chooses some other path, chooses to react with another substrate that is present in the reaction medium, more reactive than nitrobenzene, and it reacts with that. So these are the problems that we have associated with our Friedel-Crafts reaction. So let's see how some of these have been taken care of. One is a solid state reaction. So what is the solid state Friedel-Crafts? Traditional catalyst that is used for linear alkyl benzene, we have talked about this, is HF. It's very bad, but this has been replaced. Now you can use silica alumina catalyst, which has been fluorided, and this does not require any sort of special container or anything like that, because it is not that corrosive. Operating cost is also lower, and to isolate the product and finally get rid of the fluoride, if you are using HF, you need to have an acid scrubbing system, a complete waste disposal system of the calcium fluoride that is generated from it. No such thing actually is needed for this type of catalyst. They have developed a new generation of catalyst, Lewis acid catalyst, which are known as micro encapsulated Lewis acids. What do you understand when I say encapsulation? What is encapsulation? Encapsulation means confinement within a space, right? So they have developed polymeric material within which they can embed, integrate Lewis acid catalysts. Inside a polymer, it forms like a capsule, and the catalyst remains there. The monomeric Lewis acid catalyst like AlCl3 or FeCl3, those have been replaced because they have corrosive properties by this type of micro encapsulated Lewis catalyst. One such example I have given here. This MC means this is micro encapsulated. This is a scandium salt of triflic acid. Okay, so we are using acetic anhydride as your electrophile, anisole as your nucleophile. The reaction is done in nitromethane solvent, and a salt is added to improve probably the solubility or something like that. The reaction takes about 6 hours, so that's not very ideal, but it can be done at 50 degrees centigrade. So that's just around above the room temperature compared to the summer temperatures that we have here. And methoxy is a orthopara directing group, so we get this compound in good yields. Another method they have developed involves a zinc chloride exchange K10 montmorillonite. This is a clay. The people call this thing clay zinc, and this clay zinc has been found to induce Friedel-Crafts reactions where the aromatic substrate is reacted with not only alkyl halides, because alkyl halide, you know that alkyl halide is traditionally been used as the electrophile in Friedel-Crafts reaction since the inception of the reaction itself. But you can modify the method by using clay zinc, where it gives you sufficient substrate scope, or I should say reagent scope, where you can use the aldehyde as your electrophile, or you can use the alcohols as your electrophile. So that gives you some kind of a flexibility. One example that for clay zinc that we have given here, this reaction is done in chlorobenzene medium at 132 degrees centigrade. This is formation of a thiophene derivative. The electrophile is basically, can you identify the group? What is the group here? What sort of a functional group is that? Yep.
Acetal.
Yeah, it's an acetal. So with clay zinc, you can generate the electrophile there, and this ring will close down the 5-membered ring and give you a corresponding benzothiophene, right? They are, some other catalysts are found to induce polymerization, particularly with this substrate, this benzothiophene precursor. But for clay zinc, the polymerization is stopped, and it is believed that within its confines, the cavities that is, or the pores that is present in clay zinc, this substrate gets confined and reacts, does not get the opportunity to meet other substrates, and therefore polymerization is stopped. So these are all like solid phase, solid state reactions. So what is the green context? For sure, we are using kind of a solvent free condition. Polymerization has been avoided, product isolation is easy, and therefore waste treatment problem has also been avoided. We can use aldehydes, alcohols as our electrophiles, so that gives us more reagent scope as well. Next is ultrasound assisted reaction. This is a substrate where there are several groups present on the aromatic ring. This time they are using acetyl chloride as your electrophile, and this OH is the one which will actually direct the incoming electrophile, and the only two vacant positions are here. and if R is not a sort of a good Lewin group in terms of cation, then there is no sort of a ipso substitution. So either this at this position or at this position we will get the introduction of the acetyl group. So this means sonication. We are using AlCl3 as catalyst, diethyl ether as solvent, and isopropylamine is present as the base to mop up any proton that is coming out of the reaction. Same thing can be done with this one, where the OH again directs the incoming electrophile ortho to it. These two positions are for sure equivalent, and you can see there is a present OH in this reaction, but under sonication this OH is not interfering with the reaction. Otherwise it would have complexed with the AlCl3 and it would have led to further complications. Next up is an important electrophile. Here you have two electrophilic sites. One is this one and the other is this one. From the product, can you identify the part or the 4 carbons that have come from the electrophile? Can you identify that? Yeah, this whole part is coming from, this is a 4 carbon unit, 1, 2, 3, and the methyl is 4. So that's the 4 carbon unit, 1, 2, 3 and 4. So first this one is reacting, then this one is also reacting after this aromatic electrophilic substitution is over, and eventually we will get the fused ring system from which we can further manipulate this carbonyl and functionalize this whole system. So under sonication you can do all these reactions. Waste treatment problem is avoided. Reaction is under ultrasound, which is a sustainable and green energy source, and therefore the energy efficiency is high. The reaction furnishes good yield, occurs in short time. The next section deals with something which is very fascinating, something known as near critical water, NCW. There are many synonyms of this NCW thing. Some people call it high temp water, some people call it hot water, because when you say hot water it doesn't make much sense, but you will see that this is something really different. You can call it subcritical water or near subcritical water. People have different names for it, but we will have this near critical water or NCW in short to depict this thing. Liquid water, if you increase the pressure on it, what will happen to its boiling point? If you increase the pressure on some sample of water that you have, what will happen to the boiling point of that sample of water? How does the boiling point vary if you of a liquid if you increase the pressure on it? Does the boiling point remain the same or it changes? Let me give you an hint. When you are in a hilly area like Darjeeling, you have to use pressure cooker to cook your food. Why do you think?
Current boiling point increase when pressure increase.
No. Let me ask you this again. Do you think that air pressure is higher when the altitude increases or it decreases? When the altitude increases, is the air pressure higher compared to in the plain area, or is the pressure less? In hilly area, pressure is higher.
Height increase pressure.
So what happens to the air that is between the hilly area and the plains? Does it have no weight? As altitude increases, pressure decreases, and because it decreases, the boiling point of liquid also decreases, right? And so basically you are cooking your dal when the water boils at 100 degrees centigrade when you are in Kolkata, and it takes about 15 minutes to completely cook the dal. But if the boiling point of the same water is only 80 degrees centigrade, then would your meal be ready within 15 minutes? So you have to cook longer, and that will lead to more consumption of LPG. And so what do? To save fuel, to save energy, to save time, you use pressure cooker. Artificially increase the pressure on the water that contains the dal, and therefore the boiling point increases and you are happy. Right? Makes sense, na? So if you increase the pressure, the boiling point increases, and for every liquid there exists a temperature above which, no matter how much pressure you apply, the corresponding vapor cannot be liquefied, and that's called the critical temperature, right?
Yes, sir.
For water, the critical temperature is 374 degrees centigrade and the critical pressure is 221 bar. That means at critical temperature you have to use at least 221 bar, or 1 bar is approximately 1 atmosphere, almost 220 atmosphere pressure, to liquefy the corresponding water vapor into water, right? So then if you have water which has a pressure on it like 40 to 90 atmosphere or bar, then the boiling point of that water is much higher than 100 degrees centigrade, and it's about in the range of 250 to 350 degrees centigrade. At this temperature and pressure, the physical and chemical properties of water is completely different from the water that you see at 1 atmospheric pressure, the boiling point of which is 100 degrees centigrade. Mainly two things will happen. Because this is not exactly the critical stage, we call it near critical stage or subcritical stage, just below the critical stage. But as we go on increasing the temperature, as you go on increasing the pressure and subsequently the temperature of the water, the dielectric constant actually decreases. At ambient condition, that means at room temperature, the dielectric constant is 80, and that makes water one of the most polar reagents or most polar solvents that is used in chemistry, and ideal candidate to solubilize salts. We have talked about this. But if you manage to increase the temperature of water at 275 degrees centigrade, can you do that at 1 atmospheric pressure? Can you have water at 275 degrees centigrade in liquid state when the pressure is 1 atmosphere? Absolutely no, everything will be vaporized. So you have to increase the pressure on it so that the temperature can be sustained. But then that value of 80 drops to only 20, see? So what happens? The dielectric constant decreases. And this is quite in the range of the compounds which are known as the polar organic solvents. So as the dielectric constant decreases, the polarity of water decreases, and therefore it becomes like ideally suited for organic compounds to be solubilized in it. Non-polar organic compounds are not soluble in water because water is a polar solvent. But if you manage to decrease the polarity of the solvent, then should the solubility of the non-polar organic compound increase or decrease? You have managed to lower the dielectric constant from 80 to 20. The water has now become more like acetone. So it will now be able to solvate the organic compounds much more easily. But it is still, the epsilon value is still, the dielectric constant is still high enough so that it can dissolve and ionize salts. So that gives me a common ground where the organic compound can also come and interact with the ionic reagent that I am using. So that is one thing. Then after the reaction is over, you decrease the pressure and you decrease the temperature, so water comes down to its normal state and it then becomes polar again, and your organic byproduct or the organic product that you have formed, which was soluble in the near critical water, is now separated from it and gets precipitated. So your separation is also very easy. Another important aspect of near critical water is that the dissociation constant actually changes. The dissociation constant of water changes. At say 250 degree centigrade, the dissociation of water, the dissociation is threefold increased. That means the concentration of H plus and OH minus in that water is 3 times than normal water, and that gives us an opportunity to use that medium as either an acid catalyst or a base catalyst without actually adding any sort of acid or base from outside. Now that's very good, because if you are using acid or base, then finally a neutralization step has to be done, which may lead to, for per kg of product, maybe 1 kg of salt is being produced in the reaction medium. But we can get rid of all these things if you increase near critical water, if you use near critical water, which itself by virtue of the higher dissociation constant can act as the acid or the base catalyst as is required. So near critical water is very, very important, and it's a fascinating aspect of green chemistry. And you will see about these things: supercritical carbon dioxide, near critical water, green solvents or their modifications. Sir will talk about these things in his class. So they have this near critical water thing which can done wonders to our organic reactions. So one of the reactions in Friedel-Crafts is alkylation of phenol, where you are doing the reaction with either isobutylene or tertiary butanol, which generates the tertiary butyl cation. Now, phenol is an ambident electrophile. It can react with oxygen, it can react with carbon under certain circumstance. When you are using excess of phenol in large excess, you get the corresponding ortho or para substituted product. Similarly, paracresol can also react between methyl and OH. OH is obviously a higher activator, more activator, and therefore the incoming electrophile will be directed ortho to OH, and they have done this reaction with near critical water. This has also been done in acylating of phenols. Phenols and resorcinol have been successfully acylated using either acetic acid in near critical water or in neat acetic acid, where the temperature is increased to 250 to 300 degrees centigrade. Obviously pressure has been increased as well, and no catalyst is needed. However, in this case the yield is somehow low, because the O acylation is quite prevalent. We get some of this thing, but these mono O acylated or di O acylated products are also there. Buffer induced Friedel-Crafts acylation has been accomplished when we are doing this thing in indole. So this time we are using some buffer, and we are using half aldehyde, half ester as our electrophile. And as we know that indole directs in its electrophiles onto the C2 or the beta carbon. Metal triplets has been in water has been used to replace the conventional catalyst. This thing is quite interesting. This is a scandium tris dodecyl sulfate. So you have the ligand is oxygen bonded with sulfur, sulfur bonded with 2 double bonded oxygen and 1 single bonded oxygen. This single bonded oxygen has a long aliphatic chain, a 12 carbon aliphatic chain. 3 such ligands on scandium 3 in water. You can do the reaction at room temperature. Within 1 hour you will get alkylation here using methyl vinyl ketone, while basically you are targeting to do a Michael type of reaction. We can also use indium triplet as a viable catalyst for this step. And what about green context? Green solvent, for sure, near critical water is a green solvent, water is a green solvent, waste treatment is avoided, selectivity and the alkylation, selectivity of the alkylation is far superior compared to conventional reagents that we have used. Finally, another green solvent is ionic liquid, where Friedel-Crafts reaction has been done with naphthalene. We get both the alpha as well as the beta products, and reaction occurs in green solvent. We can recover the catalyst and reuse the catalyst if you use amine chloride as your reaction medium. Waste formation is ensured and the yield of the reaction is very high. So this completes our name reactions that is outlined in the syllabus, of which we are supposed to learn of the green aspects of those reactions. But next class we will be talking about some rearrangement reactions. Do you have any questions from today's class? If there is no question, then I stop the recording here.